As for the little fuser demonstration today, we're gonna have to look at some basics. First of all, the fuser is a little fusion reactor, a nuclear fusion reactor. So, nuclear reactions, similar to what happens in the sun, are occurring. First of all, we have a fuel. That is, you basically know hydrogen. Hydrogen is the smallest of atoms, basically. It's just one proton and one electron. There are also isotopes of hydrogen that have more than just this one proton. They also have a neutron, or two neutrons, that would be tritium. But with one proton and one neutron, you have deuterium, which is the fuel used in this case, the nuclear fuel. What basically happens is that you have the reactor core itself, the fuser. That is a chamber that can sustain a very high vacuum, about 10 to the power of minus 6, or sometimes 10 to the power of minus 7 torr. Very strong vacuum. What you do then is insert some of these deuterium atoms into the vacuum chamber, and there will also be an electrode inside and an applied high voltage. Now what the high voltage will do is sort of heat up the atoms, accelerate them, our little deuterium atoms, and it will also just strip off the electrons of them. So it will just be the bare core, it will just be the proton and the neutron without an electron shell, and this state of matter is called a plasma. So in this plasma, with very high temperatures, like at least 5 kilovolts, but we're going towards about 54 kilovolts if I remember, the atoms will be in this state without the electrons, and they will be forced into each other and fuse together. So basically we have two of these atoms, two of these deuterium atoms without the electrons, as they were pulled off already, and due to the intense temperature they can overcome the Coulomb forces, which usually prevents atoms from bumping into each other, and they can form a new atom. That will be, of course, the two protons, the two neutrons. So that will be, in the end, if it will be done, it would have two electron shells, but we can actually forget about that for now. It's just the nucleus for now, which is two protons and two neutrons, but it's in a very high energy state. So what usually happens to this now helium-4 atom, because we have if there's one proton in the core, it's hydrogen. If there's two protons in the core, it's a helium atom. So, and that stands for the isotope. We have 1, 2, 3, 4 nucleons in the core, so this is helium-4 for now. What now happens is, because this is really in an excited state, the little atom is in an excited state, and what happens is that usually a neutron gets ejected. A neutron with a very high energy, about 2 mega electron volts. Or what can also happen is that a proton is ejected, or it could stay like that and a gamma ray is ejected. So if the gamma ray is ejected, that would leave us with helium-4. If a neutron is ejected, we still have two protons, one neutron, so that would be helium isotope 3. Or we could also have the proton ejected, which would basically have us go back to the hydrogen. So we have one proton, two neutrons, and that would be tritium. Tritium, the radioactive isotope of hydrogen. That is basically what can be produced. As far as I know, what happens mostly is that neutrons get ejected, and with neutrons you can cause further nuclear transmutations, because if neutrons get absorbed by another atom, then funny stuff happens. We'll look at that later. But now let's look at John's beautiful fuser. Here's my Gamma Scout.
Throttle valve.
Alright, let's see.
Close the throttle valve. deuterium supply.
That's the nuclear fuel, as you remember. High voltage being applied. Picking something up already. The red number in the background is neutron counts per second. Nothing measurable with my Gamma Scout yet, as it cannot measure neutron radiation. Yeah, this one isn't picking up anything, it's just the neutrons. This run was at 40 some kV, so the X-rays are too weak to reach the Gamma Scout. Oh yeah, I forgot to mention that, right? The X-rays. So we talked about the high voltage pulling off electrons from the hydrogen atoms, from the deuterium atoms, and, well, you know, you probably remember that from one of my older videos about how X-rays are generated. That in an X-ray tube, well, that's a lousy tube. Anyway, there's an anode and a cathode, and an applied high voltage on the anode will accelerate electrons, which is just basically the power that comes out of your power socket. The American socket would look like this. That's rather funny actually, but anyway. The electrons will get accelerated towards the anode material, and then there they will be decelerated and cause Bremsstrahlung, braking radiation, and also characteristic X-rays. But anyway, you know that electrons, if they are really fast, if there's a high voltage applied, and electrons get pulled somewhere and they decelerate again because they're really fast, then X-rays are produced. So we get a lot of X-rays from all these electrons flying about.
I mean, the REM ball. Yeah. Like if I remove that, the count rate on this thing will be much higher because it absorbs a lot of the neutrons.
Oh, okay.
It's kind of in the line of sight between this and the other two detectors.
Yeah, that's true. Makes sense. Yeah. The RAM ball is the neutron detector that is behind the lead wall. You can see it on the left there. It's just next to the fuser.
Yeah, output's kind of weak.
Still, hardly any X-rays here. You can hear the neutron counter go mad, but hardly any X-rays. That is because the X-rays are easily shielded by the lead, and the neutrons just don't care about that kind of shielding. But yeah, when you get close, of course you can detect X-rays, like these two devices.
Oh, yeah.
Still not so much. Not from the radiation a Geiger-Müller tube can detect anyway. It's about 60 microsievert.
That's about 43 kV. Let me turn this thing off. It's irritating.
Yeah, a bit loud.
Man. Yeah.
Here's a look at the reactor itself, the fuser, which is just a little ball there. On the left you can see the connected high voltage. Cover, like if you got a piece of aluminum foil, I could put over here so you can only see the flashes from striking radiation. That would be ideal, I guess. Yep, that works. Neutron radiation and X radiation striking the poor little camera again. Now back to the other view. Here's another close look at the actual core where the nuclear transmutation occurs. Occurs in there, sealed up in this steel ball. Yeah, okay, that'll be fine. And yet for another run, cranking up the voltage a bit more, and also activating silver foil. Neutron counter shows nothing is going on as the fuser is off, but this will change soon. Here we go, neutrons. That's just the neutrons arriving at the back of that shelf with the electronics, by the way. Not much picks up on there. This is a moderator substance, hydrogen moderator. Let's look at that actually. So here's the neutron again. And it's a very fast neutron. It has 2 mega-electron volts. The neutron that has been ejected from the fusor, from the core of the newly formed helium-4 atom that resulted as the fusion of 2 deuterium atoms. So we have this very fast neutron here. And some atoms, like for example a really heavy atom like uranium-238, they actually like fast neutrons and will gladly take them into their core. But other atoms, like for example a little silver atom, a lighter atom, will not like these fast electrons and they will just go by unnoticed. So what we need to do in order to cause a reaction with the silver atom, for example, we need to moderate this neutron to a so-called thermal neutron. Because 2 mega-electron volts, that's a fast neutron, and a thermal neutron, I actually have to look up the exact energy because I don't remember what thermal energy is again. We'll have to look that up and put it in later. Anyway, we slow it down to a thermal neutron by using, once again, hydrogen atoms, little protons that will be in the way of the neutron, and the neutron will sort of bump into them and scatter around them, and while it does that, it will lose energy. You can imagine like a little bouncing ball you throw on the floor, and it will first of all will jump high and then lower and lower and lower because it loses energy, and that's sort of what happens with the neutron as well. The fast neutron will lose energy and become a thermal neutron, and this thermal neutron will then be taken up by the silver isotope, by the natural silver, and if that happens, the silver atom will have 1 more neutron. So what can happen is, it depends on the isotope. Some isotopes are still stable if you put in 1 more neutron, but what happens with the silver is that we get 2 different isotopes. One isotope has a half-life of 15 seconds, and the other isotope has a half-life of roughly 2.4 minutes. The cross-section for absorbing thermal neutrons of the one isotope of silver that produces the radioisotope of 15 seconds is much more likely to occur because of the greater cross-section, which is determined in barns. That's the unit for the chance of a nucleus to absorb a thermal neutron, than that of the other silver isotope, which is existent in natural silver, which has a half-life of 2.5 minutes. So when we activate silver, we can actually see that given a few half-lives of this isotope, we will hardly be able to detect anything because this occurrence is much lower, and, well, of course, you need much more of the radioactive atoms in order to measure the same amount of activity because of the different half-life. But, as I said, also, this reaction is less likely to occur than this reaction because of the better cross-section in barns. I hope it sort of made sense, but you can always Google for more info, I guess. This video is long enough as it is, so let's look at the activation products. So here the neutron oven is baking us nice little radioactive silver with the moderator substance being removed, and this sheet of silver that used to be not radioactive is pretty much radioactive, as you can see now. Pay close attention to the clicks. As you will hear, they will cease very quickly. As I said, because the main activation product actually has a half-life of just 15 seconds. The main resulting radioisotope of silver.
We can already see or more like hear how the count rate is dropping.
So most of the silver atoms get rid of the excess neutron by converting it into a proton, which is the beta minus decay electron emission, and become cadmium.
That is so cool.
Yeah, indeed.
So this is neutron activation and nucleosynthesis. You put a neutron into silver atoms and thus make the silver atoms radioactive, so they decay into another element into cadmium, which will be stable. Pretty cool, eh?
10 to the 7th neutrons. That thing was on, and it put it up a range on times 100 and about.
Whoa, so it was on scale on the times 10.
Yeah, like 120 millirem or something.
Whoa. Yeah, that's a lot of neutron radiation indeed.
So, with the silver having decayed, let's have a look at another fusor run at, I think, something around 55 kV, so that'll output a lot of radiation, neutron and X radiation.
Yeah, definitely a few more X-rays here now.
The X-rays have much higher energies and are much more penetrating and thus can get through the lead shield, but not many of them get through the lead shield, which you will see in a second. Seems like 6 microsieverts power is a lot, but it's quite a good amount of shielding if you compare it to what happens if you get really close. Also have to take the inverse correllar into consideration, but still, the shielding is quite good.
Could just put the 55 here as well.
Will be full.
Yeah. Oh yeah, man.
Let's see what it's about 40.
That's around 500 neutrons a second. A little less.
Yeah, it's over double. We had about 18 to 20 millirem, and now it's like 44, 48
Yep.
millirem.
But definitely quite a lot of X-rays here, so that's a significant increase.
Yeah, it's up there. It's really
Oh, let's see how this thing reacts to it. Takes a while to adjust, but oh yeah, we're in the millisievert range now. Well, it's just my hand in there, so nothing too bad. Yeah, takes a while to adjust, but should be still growing.
The voltage dropped a little bit too. Down to 52, 53 kV.
Alright.
52. Yeah.
Still about 2.1 millisievert.